So we will see. Okay, before I move on, any student have any questions based on last class? If anyone has any clarification or queries, questions, please let me know. Then I can answer in a few minutes. Then I will continue. Okay, so it looks like there are no questions. Maybe you haven't gone through the discussion. So just quick review of what we discussed in the last class. Hope you're able to see my screen.
Yes, sir.
Yes, sir.
I hope students are able to see my screen.
Yes,
Okay. So we have basically two types of pneumatic transport: dilute phase and dense phase. Dilute phase, where particle concentration, the solids concentration is very low, whereas in the dense phase concentration, solids concentration will be higher and air velocity will be lower, or the gas velocity will be lower. Whereas dilute phase concentration, solids concentration is low and velocity of air is high. So that is the simple way. In dilute phase pneumatic transport, if you are transporting through the vertical pipes, that is vertical type dilute phase pneumatic transport. If you are transporting the solids through horizontal pipe, that will be the horizontal type dilute phase pneumatic transport. Now, in the last class, we have seen in case of vertical type dilute phase pneumatic transport, we will have a critical velocity called choking velocity. I have mentioned in the last class what is choking velocity. The velocity of the gas should be 1.5 times this choking velocity to avoid any such unwanted conditions like choking. So these are the equations, correlation we need to use to find out the choking velocity. UCH is the choking velocity. So we have to solve simultaneously these two equations, these two expressions to find out choking velocity. Then we have horizontal type dilute pneumatic transport. In a horizontal pneumatic transport, we will have a critical condition called salting. So the saltation velocity we can estimate using this expression, and here U salt will be the saltation velocity. Just like vertical transport, in the horizontal transport, the gas velocity has to be 1.5 times the saltation velocity. So up to this part, I have explained in the last class. So students are able to see my slides?
Yes, sir.
Can anyone tell me?
Yes, sir. Yes, sir. We're able to see it.
Yes, sir.
Yes, sir. Yeah, thank you. So in the last class, I talked about this word called fluidization, but I thought it may not be clear. So I'm giving a small explanation on fluidization. This is called fluidization. This is one phenomenon. Then pneumatic transport. This is another phenomenon. but usually these two are related. Usually these two are related. So I wanted to explain what is fluidization. I wanted to explain what is pneumatic transport. What are the differences? And in this course, we'll only talk about the solids transport. So we'll only discuss pneumatic transport. We won't go through fluidization in detail. So this will be covered in some other courses. So let's say there is a cylindrical pipe. Yeah, let's say there is a cylindrical pipe and we have a supporting or distributor plate. I have explained in the last class how the typical distributor plate looks like. Suppose if you pour solids in this cylinder, we call it as a bed of solids. We call it as a bed of solids. And since these solids are stationary, we are packing this cylindrical column. We are packing this cylindrical column with solids. This is called packed bed. This is called packed bed. We have a cylindrical pipe. At the bottom, we have a distributor plate. Then we just pour solids. And solids are stationary. And it's like simply packing a solid column, a cylindrical column. Hence, this is called as a typical packed bed. Let's say we are introducing a gas with certain velocity. Let's say we are introducing gas at certain velocity through this bed, So here I show set of diagrams and where the velocity or the flow rate of the gas is increasing as it progresses, So this is the second one. Here we have the same packed bed. And we have introduced a gas. Here we have introduced a gas through this packed bed. But the velocity or the flow rate of the gas is very low. The velocity or the flow rate of gas is very low. At that time, what will happen? The gas will slowly permeate through the void spaces without causing any movement in the particles. The gas will permeate through the void spaces present in the particles without causing any momentum to the particles. Why this happens? There are three forces acts on the particles. One is gravitational force act on the downward gravitational force, and the other forces acts on the solids by the fluid in the opposite direction. That is called drag force. You will learn more detail about drag force in fluid mechanics, drag force and buoyancy forces. Buoyancy forces. So this is gravity. So when the gravitational force acts on the solids, dominates the drag force and buoyancy force. So the force offered by the gas on the solid particles are not enough so that the solids will not move. What type of bed this is called? Can anyone say? What type of bed this will be called? In this case also the solids remain stationary. What type of bed this is called? Can anyone guess? It seems no one is responding to it. So this is also called as packed bed because solids are stationary. So if I increase velocity higher, some more higher value, at one condition, at one condition, what we'll observe is that the particles are slightly moved. The particles are slightly moved. The particles are slightly moved. Then at that time, what will happen is that the particles will be slightly lifted, but it won't, the height of the bed will not increase very high, very small increase, very light, slight increase in the height. Bed height means the height of the particles. This is called bed height. This is called bed height. Bed height. Bed height. Bed height will increase, but very small. Another important phenomena we will observe is that the solids rotate wherever they are. The solids tend to rotate wherever they are. This here, the solids are no more stationary. They tend to move along with the fluid. They tend to move along with the fluid. Such phenomena, when the particles tend to move along with the fluid or behaves like a fluid, the particles tend to behaves like a fluid, tend to behave like a fluid. Such when the solids tend to behave like fluid, that is called fluidization. When solid particles tend to behave like a fluid or move along with the fluid, that is called fluidization. Here, the fluidization is just about to start, and such state is called minimum fluidization. Minimum fluidization. So, to estimate the pressure drop across minimum fluidization, we have a famous equation called Ergon Equation. You will learn in fluid mechanics. You will learn the derivation and all those details in the fluid mechanics. Ergon Equation to estimate the delta P. Now, if I increase velocity higher than this minimum fluidization velocity, if I increase the velocity of the fluid higher than the minimum fluidization condition, what you'll observe, the particles tend to move a little more height. The bed height will increase. Suddenly, the bed height will increase. Suddenly, the bed height will increase. But it will be limited to certain height. It will be limited to certain height. Bed height will increase, but the height will be limited to certain height. The height will be limited to certain height. That depends upon the velocity. That depends upon the velocity. Usually, we wanted the particles to stay in the column, whatever cylinder column we are using. The particles we wanted to be they should stay within the column height, bed height. Here, the particles tend to behave like a fluid. They move like a fluid. They interact like a fluid. Such phenomena is called fluidization. In fluidization, the bed height have a limit. The bed height have a limit. It will have certain maximum height. It will have certain maximum height. So it depends upon the particle type, different types of fluidization observed. People have observed depends upon the interaction forces between the particles, depends upon the interaction or adhesive forces between the particles. Different types of fluidization types are observed, but those will be discussed in the fluidization. Again, I said this course is not talks about fluidization. Okay. In this course, we're only interested in pneumatic transport. So my discussion is only limited to pneumatic transport. I'm not going to the fluidization. The fluidization will be covered in other topics like fluid mechanics and reaction engineering. And it's because itself is a specialized subject. So, but I want you to understand what is the difference between packed bed fluidization, minimum fluidization condition, and pneumatic transport. Okay. When the relative velocity, slip velocity or relative velocity, when the slip velocity or relative velocity is greater than the terminal velocity. What is terminal velocity?
So the velocity of the gas at which fluidization starts,
Sorry,
the minimum velocity at which fluidization starts, minimum velocity of gas.
that is called terminal velocity.
Yes, that's what you said in last class, I guess.
No, what I said in last class is the steady velocity of the particles attained is the steady velocity with which the particle tend to move is called terminal velocity. So please, maybe there is some miscommunication, or when I said maybe I pronounced wrong, I don't know. Maybe I haven't said like this. Kindly go through, but clarification is that the velocity at which fluidization takes place is not terminal velocity. Okay, the velocity at which fluidization takes place is not a terminal velocity. I will explain terminal velocity after 2 seconds. If the velocity of the gas is much higher, student, do you have anything to discuss? Otherwise, kindly mute. Harshit Patel, you wanted to ask something? Yeah, thank you. So, if I increase the velocity further, such that the relative velocity between the solids and gas is higher than terminal velocity, what will happen is the particle's bed height will not be limited to certain height. The bed height will not be limited to certain height. Rather, the particles move along with the fluid continuously. Wherever the fluid goes, the particles also will go. Wherever the fluid goes, the particles will go. In case of fluidization, the particles will not go along with the fluid. The particles will be lifted to certain height. The particles will be lifted to certain height. But at this condition, the particles move along with the fluid. The particles move along with the fluid. Wherever fluid goes, the particles also will go. This is called pneumatic transport. This is called pneumatic transport. This is called pneumatic transport. The last diagram is basically describes the pneumatic transport. Now, when the velocity of the fluid is such, when the, as you increase the gas velocity, the particle velocity increases. The particle velocity increases. In case of fluidization, the particles will have certain velocity. Okay, but at beyond certain distance, the velocity of the particles will become zero. Beyond certain distance, the particles will not have any change in momentum. The particles will not have any acceleration. The particles will not have any the particle will accelerate certain thing. The particle will accelerate certain thing, but there's only limited to certain height. But when at certain condition, the particles will attain a constant velocity with which the particle move along with the fluid. The particle will attain certain constant velocity with which the particle will move. That is called terminal velocity. That is called terminal velocity. In the dilute phase pneumatic transport, the slip velocity or the relative velocity. What is slip velocity? The velocity difference between gas and particles. The velocity difference between the gas and particles is much more higher than the terminal velocity. Much more higher than the terminal velocity in case of dilute phase pneumatic transport. In case of dense phase pneumatic transport, that will be closer to terminal velocity. That will be closer to the terminal. Still it's higher, but closer to terminal velocity. Do you understood terminal velocity? The student who said the fluidization velocity. There is a difference between fluidization velocity and the terminal velocity. In the terminal velocity, particle will attain constant velocity. The acceleration will be zero.
Sir, can you please say 1 second?
Sorry?
Sir, can you please say 1 second? I haven't understand.
Okay. So in case of fluidization, when increase the gas velocity, the particles will be lifted to certain height. Okay. So it can only move up to this point. It cannot move beyond this point. Okay, because it is not attained. It is not attained a constant velocity with which the particle can move along with the fluid. But at this conditions, if I further increase the gas velocity, the particles will attain certain velocity with which a certain constant velocity with which the particles will move along with the fluid, right? Terminal velocity is nothing but a constant velocity attained by the particle. A constant velocity attained by the particle with which the particles will move along with the fluid. In case of fluidization, the particles will move up to certain height and particles will rotate. The particles will rotate. The particles will have certain amount of acceleration because of the resistance. But here, in case of terminal velocity, the particles will not offer any resistance. The particle just free flow. The particle just move along with the fluid with certain constant velocity. At terminal velocity conditions, the particles will move with certain constant velocity. Understood?
Yes, sir.
Since it's a constant velocity, since particle attains a constant velocity, rate of change of momentum, rate of change of momentum g m dot v or mv dot or d square mv by dt square or acceleration is zero. It is steady velocity. Acceleration is zero because it attains a constant and steady velocity. Hope I could explain. Hope you understood.
Sir,
Yeah.
sir, I had
sir.
a doubt. Sir, in case of dilute, the slip velocity is equal to terminal, but in case of denser, it is slightly greater.
No. In case of dilute phase pneumatic transport, the slip velocity will be very high, maybe 10 times, 11 times, or much more higher than the terminal velocity. In case of dense phase, velocity will be lower, right? So that will be 2 times or 3 times the terminal velocity. Understood?
Okay, sir. Yes, sir, got it.
In dilute, slip velocity will be very high than terminal velocity. Very high means 10 to 15 times or more. 10 to 15 times. In case of dense, it will be close to terminal velocity, that may be 2 times or 3 times the terminal velocity. Did I answer your question? Other student who asked this one?
Yes, sir, got it.
Or did I miss your question?
Sir, got it, sir. I just wanted to know the relation, that's it.
Yeah. Okay. Thank you. So hope all of you understood the difference between fluidization and the pneumatic transport. It is very, very important. You will see the packed bed in mass transfer. Often in packed bed, we will see mass transfer in detail. Mass transfer course. You will come to know about packed bed. So most of the mass transfer operations, we tend to use packed beds. Fluidization, we will see in, you will learn more in reaction engineering, especially catalytic reactions. Fluidization, we don't want catalyst to go along with the fluid, right? We wanted the catalyst to stay in the reactor. So most of the often fluidization is predominantly used in the reaction engineering. Reaction engineering, especially when you use catalytic reactions. solid catalytic reaction. If reactant is gas, and if you need to use solids, of reactant is gas or liquid, if you need to use solid catalyst particle, we don't want particles to go away out of the reactor. We don't want particles to go out of the reactor. We wanted particles to stay within the reactor. So there, we wanted particles to move only up to certain height. We wanted particles to move up to certain height. We don't want it to go away from the reactor. So hence, in reaction engineering, especially when we use solid catalytic reactions, heterogeneous catalytic reactions, we will use fluidization. The fluidization is predominantly used. But in transport, we don't want it to limit to certain disk height. We want it to go away along with the fluid. So this is pneumatic transport. So what is the difference in pneumatic transport? The particles just move along with the fluid. So the interaction between the gas and the particles will be very low. In case of pneumatic transport, the interaction between gas and particle will be low because the particle attains a certain steady state velocity and just move along with this one. You will not see much intermixing. You will not see a lot of intermixing in case of pneumatic transport. In case of fluidization, intermixing between particle and fluid is very high because the particles rotate with certain velocity, they will have certain acceleration, and depends on the velocity changes, move up and down. So interaction between the particle and gas is very high. Hence, the particles helps as a agitator. It mixes the fluid. The particles will mix fluid thoroughly in fluidization. In case of fluidization, the particles make sure the concentration is uniform in the reactor or in the column. So that is where, in case of this one, the intermixing between particles and fluid is less. So hence the interaction between particles and gas is very minimal. Particles and gas is very minimal. That is the difference in the physics point of view. That is the difference in the physics point of view. Hope you all understood pneumatic transport and the fluidization. If anyone have questions, do ask me, because this is the important phenomenon. You should understand the difference between fluidization and the pneumatic transport. Later on, you should not say, "Sir, I didn't talk about fluidization. I don't know what it is." You should not say. You should clearly say why I'm not talking about fluidization. You should know, and what is the difference between fluidization and pneumatic transport. You should know. If anyone have any clarification here, do ask me. Number increased or not?
Sir, it is clear, sir.
Yeah, thank you, Vignesh. So, I wanted to give some quick fundamental definitions and basic formulas here. So again, I'm just talking about pneumatic transport. So in this course, we won't talk about fluidization. We'll only talk about pneumatic transport. So we have a bed of particles fed. We are continuously feeding the particles at certain mass flow rate, QT. Volumetric flow rate. This is volumetric flow rate. I have written wrong, sorry. So solids are fed through this side hooper and with a certain flow rate, volumetric flow rate. So the particles are coming and falling here into this one. Then the bed or the cylindrical pipe cross-sectional area is A. The cross-sectional area is A. And we are sending the gas with certain flow rate. This is again volumetric flow rate, meter cube per second in case of SI units. Meter cube per second in case of SI units. Okay, I'll come to that point later. So once I supply the gas with certain flow rate, where the relative velocity or the slip velocity is much more higher than the terminal velocity, the particles will move along with the fluid. The particles move along with the fluid. Okay? The particles are moving along with the fluid. Now we wanted to do some basic definitions. We wanted to know. The first one is called superficial velocity of the gas. Superficial velocity of the gas. That is nothing but velocity at the entrance. That is one way. Another way is the velocity of the gas if there is no particles in the cylindrical pipe. Velocity of the velocity of the gas if there is no particles. If there is no particles, if gas only flows through this bed, if the gas is only flowing through this cylindrical pipe, the velocity of the gas is nothing but the superficial velocity. Below the support plate, since there is no particles, the velocity of the gas will be the superficial velocity. That's why it is also called as entrance velocity. That's why it is also called as entrance velocity. So we know velocity is nothing but volumetric flow rate by area. QF is the volumetric flow rate of gas by the cross-sectional area A. Finally, we have the superficial velocity of the solids. That is velocity attained by the solids, assuming that the whole column is occupied by the only solids. This is in a figurative. We will never have an exact phenomena like this that only the particles are moving. Let's say it's in vertical pipe. You are pouring the solids from the top through this pipe. Then you can typically attain this. But from the bottom to up, you will never attain. But just to a figurative expression, that is superficial velocity of the solids is volumetric flow rate of the particles by area. The solids and particles, I think I'm using interchangeably. Probably I may miss the but solids and particles means same. Okay, kindly maybe I was not consistent with the wording here. Maybe in the rest of the slides also. But please do understand that solids, particles, powder, all means same. Although there is a slight difference in the fundamental explanation, but kindly consider it as a same. I was not consistent with my wording. Solids, particles, powder, all means same. Okay, there is no difference. So superficial velocity of the solids is nothing but if only solid flows, if there is no gas is flowing, what velocity the particles attains, with what velocity the particles will move. That is called superficial velocity. Superficial velocity is nothing but volumetric flow rate of the particles by area. Now, during the pneumatic transport or during the fluidization, you can see you can see that this column, the cylindrical pipe, is occupied with two things. One is voids, that is gas volume. Another one is solids volume. Another one is solids volume. So here we define void fraction. Void fraction is nothing but the voids volume, the spaces between the particles, the volume of the spaces between the particles by the total volume. So in the pneumatic transport, we'll assume that the particles are distributed uniformly. The particles are distributed uniformly in the gas. So if you take any cross section, that represents the same throughout the pipe. If you take any small area of cross section, that represents the throughout the cylindrical pipe because the particles are uniformly distributed. So we can calculate void fraction of any small area. Suppose if I take the small area, I can easily calculate this is the solids volume and remaining is voids volume. So void fraction is about the voids volume. So these are the voids. Hope you all understood. So this is if you take cross section, these are all voids. Whatever I highlighted the blue one, these are the voids, empty spaces. or the volume occupied by the gas. The volume occupied by the gas. The void volume is nothing but the gas volume within that cross section. And the total volume include gas volume plus particle volume. That is nothing but the void fraction. I think we already discussed in the earlier classes about the void fraction. So now, what is actual velocity of the gas? What will be the actual velocity of the gas? This is the actual velocity. Actual velocity is nothing but, see here, we know that the velocity depends upon the area. Since volumetric flow rate will not change, the velocity changes with the area. Now the gas is flowing between the void spaces. So here the velocity is UFS, superficial velocity. Here before it enters the solids, before it passes through the supporting plate, that is superficial velocity. And velocity of the gas inside this one is nothing but UF. Velocity gas inside this one. Since the gas is flowing between the void spaces, since the void area is lower than the total area, cross-sectional area, since the void area is lower than the cross-sectional area, the actual velocity will be higher than the superficial velocity. The actual velocity will be higher than the superficial velocity. UF is greater than the UFS. So how much it will be? What will be the void area? The void area will be cross-sectional area into, can anyone say what will come here? Void area will be cross-sectional area.
Say into epsilon.
What will come here?
Say epsilon.
Epsilon.
Void fraction.
Right. Correct. Thank you. So we'll get the void fraction. So actual velocity will be UF will be UF by A into epsilon. A into void fraction. Right? So QF by A we already defined as QF by A is defined as UFS. So this will be UFS by epsilon. So that is the actual velocity. Similarly, actual velocity of the particles, since if you do a void fraction is total volume, 1 minus epsilon will be, let's see, probably you know it, but let me, void volume what is total volume in the bottom? Void volume by void volume plus solid volume. Right? Total volume is nothing but void volume plus solid volume. In a given cross section, total volume of this cross section, total volume of this one will be void volume plus solid volume. So 1 minus epsilon will come what? If I do this one, void gets cancelled, then I will get solid volume, solid by total, solid by total, solid volume by total volume. So since we talk about actual velocity of the solids, it will come as UPS by 1 minus epsilon. That is superficial velocity of the particles by 1 minus epsilon, because 1 minus epsilon talks about solid volume by the actual volume. So solids area, just like this, void area is A into epsilon, solid area will be A into 1 minus epsilon. Just like void area is A into epsilon, solid area will be A into 1 minus epsilon. Hence, actual velocity of the solids will be superficial velocity of the solids over 1 minus epsilon. Then we have the mass flow rate of solids is empty. Mass flow rate of the solids is empty. We can calculate volumetric flow rate. If you multiply with density, we get the mass flow rate. This is volumetric flow rate is QP. If I multiply with density, I get the mass flow rate. This important called mass flux. Whenever you want to define flux, we have to divide with cross-sectional area. Whenever you want to define a flux, we have to divide with cross-sectional area. We have to divide with cross-sectional area. So the mass flow rate divided by cross-sectional area is nothing but the mass flux. Mass flow rate divided by the cross-sectional area is nothing but the mass flux. These are the fundamental definitions. I think all of you please understand there is something called superficial velocity, there is something called actual velocity, and how to differentiate and how to estimate the mass flux. Hope all of you understood. If anyone could not understand these simple definitions, please let me know. I'm happy to explain once again.
Excuse me, sir.
So here,
Sir,
relative velocity.
hello.
Yes, please. Yes.
So the definition we are talking on, is this a pneumatic transport or fluidization?
Sorry, pneumatic transport only. Could you repeat? All these
Sir,
definitions applicable to only pneumatic transport. That's what you're asking, no?
yes, sir. Yes, sir.
These applicable to, these are the fundamental. These applicable to fluidization, minimum fluidization, and pneumatic. For all these applicable, these formulas applicable.
Okay, sir. Thank you.
So another one is, next one is continuity equation. I think in fluid mechanics by this time you would have learned the continuity equation, right? For a fluids where the fluids with density doesn't change, what type of fluids they're called? If the fluid density doesn't change, what type of fluids they're called?
Sir, incompressible fluid.
Incompressible.
No answer. If the fluid density is
Sir,
constant,
See, incompressible fluid.
incompressible fluid.
yes, very good. If the density of the fluid doesn't change, that is called incompressible fluid. If the density of the fluid changes, that is called compressible fluids. For incompressible fluids, mass flow rate is constant. For incompressible fluids, mass flow rate is constant. Basically, that is the continuity equation says mass flow rate, m dot. So m dot equal to, in fluid mechanics you would have definitely learned, cross-sectional area into density into velocity. For a simple 1D continuity equation, m dot equal to rho in A into rho into U. Similar expression we are writing. So, anyone have question? If no question, kindly mute. You might have joined now. So for gas and for solids, we can write similar continuity equation. For gas, we have A and we have superficial velocity, because mass, it will not change, right? Mass flow will not change, whether at the entrance or whether inside, it will not change. So at the entrance, this will be cross-sectional area into velocity into density. that inside the, after crossing the distributor plate or supporting plate, where it mixes with the solid particles, the superficial velocity is nothing but the actual velocity into void fraction. So you will have A into actual velocity into void fraction into fluid density. Similarly, for the solid, since solids behaving like a fluid here, we can write the continuity equation. Same continuity equation can be applied here because the solids are behaving like fluid. These two expressions cannot be used for the fluidization. These two expressions cannot be used for, the first one can be used, but second one cannot be used for the fluidization. Because the particles are limited to certain height, they will not move just like the particles will not move like fluid continuously. Hence, the bottom expression we will not usually write for the fluidization. This is only for the pneumatic transport. This is only for the pneumatic transport. Other one can be used for the whatever condition, because the gas is moving continuously. So solids mass flow rate, MP is mass flow rate. Okay, MF is the mass flow rate of gas, fluid. MP is the mass flow rate of the particles. And here we have the fluid velocity into void fraction. Here we have taken the particle velocity. Hence, we taking the particle velocity. We have to use 1 minus epsilon because here we got this one. The particle velocity equal to superficial velocity of the particle over 1 minus epsilon. So that is where it comes from. Actual velocity of the particles into 1 minus epsilon into density of the particles. Because this is the expression, original expression, and same thing we converted to for gases and solids here. Typically solid loading is nothing but mass flow rate of the particles by the mass flow rate of the fluid, just ratio of these two. Usually the solid loading will be very low for the dilute phase pneumatic transport, and solid loading will be higher for the dense phase transport. Okay, hope you all understood. Oh. Forgot to animate. So next important one is estimating the pressure drop. Next important thing is estimating the pressure drop. I explained in the last class why pressure drop is so important, because pressure drop is talks about energy requirement, and pressure drop it relates to the if it is liquid pump, we need to pump the gas, right? We need to blow the gas, right? We need to blow the gas with certain flow rate. So for gases, we use blowers or compressors. If since pneumatic transport we only use gas, so let us not talk about liquid here. So we have to use blowers or compressors. So, but what capacity of the blower we need, and what capacity of the blower we need is will be found out from the pressure drop, because pressure drop is nothing but energy losses. Pressure drop is nothing but the energy losses, and how much energy is lost, that much energy we need to supply at the beginning. How much energy is losing, that much energy, additional energy we need to supply at the beginning. That's why pressure drop is the important criteria. So definitely you have seen in fluid mechanics, that is pressure drop derivation, Bernoulli equation or other equations come from the momentum balance. Momentum balance is what we know, the simple Newton's equation, F equal to ma. That is a steady state, steady force. But same thing can be converted for a general expression. That is, net forces acting on an element will be equal to rate of increase of momentum of the contents in that element. Actually, I should show this one first, but I think I didn't animate properly. That's why this content came. So let us understand. Let's say this is a pipe, and which is inclined with certain angle. Is inclined with certain angle. Through this pipe, gas and solid particles are moving. gas and solid particles are moving through this pipe. Gas and solid particles are moving. So we wanted to know the pressure drop. We wanted to know the pressure drop. That is, if you want to know pressure drop, what is pressure drop? Pressure at the inlet. This is inlet, and pressure at the outlet. The difference between these two will be the overall pressure drop. The difference between these two will be the overall pressure drop. So whenever we wanted to find out for overall, overall one, first of all we will take a small element. We will take a small element. We will do the balances there. Then we will integrate to get the overall expression. Then we will integrate to get the overall expression. Right? That is the standard phenomenon we follow. Hope you aware it. Otherwise, if you want me to explain why we are using small element, I can explain also. Hope you all know it because you might have done such definition that derivations a lot. So I'm not going why we have to choose small element and all those things. If you think you don't not clear, I can explain. Good. So you all know is why are we considering small element? I'm sure you know it. Because definitely you are all brilliant. So we have taken a small element. Here I'm assuming that the velocity or the variation is only in the axial direction, the flow direction. The variations of velocities, variations of pressure is only taking place in the actual direction. We know that pressure at any point is constant. We know that pressure at any radial point is constant. We know that the pressure at any radial point is constant. So we can make an assumption that the variation is taking place only in the axial direction, the flow direction. The variations that take place only in the, let's say this is Z direction, flow direction, and this is radial direction R. So we know that the pressure doesn't change along the radius at any plane like this. But whereas velocity, pressure, everything changes along the flow direction, that is Z direction, actual direction, right? That's why we have taken the small element in the actual direction without changing the radial direction, So that's the element part. Why we need why have we taken the element? That is so. Fluid velocity, actual velocity of fluid before entering the element is Vf, and actual velocity of the particles before entering the element is Up. While it is moving from here to here, there is some energy losses. So the fluid velocity is changed because of the resistance interaction between the fluid and solid, and particle velocity also reduced or changed because of the interaction between the particles and the solid due to either frictional losses, we can say. So here we have the fluid velocity before entering the small element is Vf. After leaving the small element is fluid velocity plus delta Uf. Similarly, particle velocity is Up. After coming out from the element will be delta Up. So why these are changing? Why they are changing? So whenever fluid flows, the fluid will have some frictional losses. The fluids will have the frictional losses. There are two types of frictional losses. You would have you learned frictional losses in fluid mechanics? Is it covered so far in your classes? Students, could anyone tell me? I'm not going to ask any questions. Just to know, is the professor taught frictional losses in the fluid mechanics course already or not? If not, he will definitely cover. But just want to know is it discussed or not?
No, sir.
Come on, students. Frictional losses. Second year, third year, anyway, no, because they already finished the fluid mechanics course.
No, sir.
No. No, yes.
No, sir.
No, sir. No, sir.
Okay, 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 no problem. So definitely there will be a good amount of discussion on the frictional losses. So whenever fluid flows, whenever let's say the fluid is flowing, and we know that when the fluid touches the wall, or the velocity at the wall will be zero. Velocity of the UF at wall is zero, because wall is a stationary one. Wall is a stationary one. Simple race, simple, we can all understand. Let's say you are running, suddenly you hit a wall. You are running, and suddenly you hit a wall. What will happen? Obviously, your velocity becomes zero, because you hit a solid object and you cannot move forward. So the fluid cannot move forward the velocity of the wall. So near the wall, at the wall, the velocity of the fluid is zero. So this we also called as no slip condition. This we also called as no slip condition. So as the fluid particles hits the wall, it loses energy. That loss of energy, energy is because of the interaction between fluid and wall. That is called wall friction. Wall friction. I'm just giving very, very blunt explanation, but of course, I'm not talking about the wrong meaning, but very, very little explanation. Whenever we have a turbulent flow, the fluid particles will intermix. Among themselves. So because of the mixing, fluid particles can interact and hit, and there will be kinetic energy losses. There will be some kinetic energy losses whenever there is a hitting between the fluid particles. Whenever there is hitting between the interaction between the fluid particles, there is some kinetic energy losses. That is called form frictional. That energy losses due to the intermixing between the fluid particles is called form friction. So because of the frictional losses, because of this friction, the fluid loses its velocity. The velocity of the fluid decreases. The velocity of the fluid tend to decrease. So that decrease in velocity, is assumed to be delta. UF. That decrease in particle velocity is assumed to be delta UV. Okay, do you all understood why this velocity is reducing? Students, do you understood my quick explanation? What is wall friction, form friction? Why is the velocity of the fluid reduces?
Yes, sir.
We also know that as we run, our energy reduces, and that's why our speed also will reduce. Similarly, the particles and the fluid also loses energy, and the velocity also reduces. That energy losses is causes the pressure losses. That energy losses results in the pressure losses. That energy losses results in the pressure losses. So pressure at the entrance of the small element is P. The pressure at the exit of the small element will be P plus delta P. Pressure at the entrance of the small element is P. Pressure at the exit of the small element is the P plus delta P. So these are the different variations. These are the how the parameters vary is given in this diagram. So net forces acting on the element. Net forces acting on the element equal to rate of increase in the momentum of the contents in the element. Rate of increase in the momentum of the contents in this element. You will see similar derivation in the fluid mechanics, and you will also see greater details of explanation in your fluid mechanics books. and definitely you will understand much more detail as you go through. But at the same time, I haven't skipped the topic. I have clearly explained whatever details necessary for you as part of this derivation. So net forces is pressure forces that is acting in the forward direction. The pressure force is acting in the forward direction. So losses, the losses, energy losses or force losses is due to the gas and wall frictional forces. That is the interaction between the gas and the wall. Energy losses are the force losses due to the solid and wall frictional losses. Solid and wall frictional losses. As I mentioned in the previous slide, in the pneumatic transport, the interaction between solid and fluid can be neglected. But whereas in fluidization, we cannot neglect the interaction between the solid and the fluid. Here I put gas and wall. I put solid and wall, but I didn't have the solid and gas. We don't have the solid and gas. But for fluidization, we will not neglect this. We have to consider because the interaction is very important. Whereas pneumatic transport, solid and gas interaction can be neglected because intermixing between particles and gas is almost negligible. We are not considering this in case of pneumatic transport. That is the difference. That is the difference between fluidization and pneumatic transport. So pressure force, gas and wall frictional forces, solid wall and frictional forces, and we all know that gravitational force. By default, since it's inclined pipe, the gravitational force is acting on this one. So this will be equal to rate of increase of momentum in the gas, because the small element contains gas and particles. So this is plus. Sorry. Rate of increase in the momentum of gas, not in gas of gas. Rate of increase in momentum of solids. So this is the simple momentum balance come from the Newton's equation. That is the Newton's expression. From the Newton's force balance, we get this momentum balance. Okay. You all understood the force balance? Students, if anyone would not understand the force balance, then kindly ask me. So we have pressure forces, gas and wall frictional forces, solid and wall frictional forces, and we have gravitational force. These are the forces acting. Then we have the rate of increase in momentum of gas, rate of increase in momentum of the solids. So we will see one by one. So here you can see change in net force. Net force means what? Inlet minus outlet. Net force means inlet minus outlet. So at the inlet we have the pressure P, and outlet we have the pressure P plus delta T. Pressure force. Pressure is nothing but force per area. P is nothing but force per area. Earlier I already showed normal force, shear force. Here pressure uses the normal force. Pressure uses the normal force. So the pressure force or normal force per unit area. Pressure is nothing but the normal force per unit area. So pressure force equal to what will come? Pressure into area. So here pressure into area. Pressure force or the normal force is nothing but the pressure into area. Net pressure force. Net is nothing but inlet minus outlet. In and out. Inlet minus outlet. So at inlet we have the T, and we have the outlet P plus delta P, and the cross section area is same. So we have P into A minus P plus delta P into A. Finally we get minus A into delta P. Why is this minus? Why is this minus coming? Because as the fluid flows, pressure reduces. As the fluid flows, pressure reduces. Hence we have the minus sign here. Hence we have the minus sign here. Gas wall frictional forces. Gas wall frictional forces. Here we have a term called FFW. Frictional forces per unit volume. Frictional forces per unit volume. This you will understand later in the fluid mechanics course, how this term coming. So I am not going in details of the how do you get these frictional forces per unit volume, because that will take so many lectures. If you want to, if I need to explain from the fundamentals. Third year students already know it, but second year students have to wait till you get your fluid mechanics course completed. So this is the frictional force per unit volume. There are, since this is a particle for the pneumatic transport, this is the particles and the fluid. This is usually multi-phase flow. Different flows are included together. One is for solids, another one is liquid. This is called multi-phase flow. We have two types of phases, two phases here. One is gas, another one is solid. Since it's multi-phase flow, and multi-phase flow is very complicated, often very difficult to derive from the fundamental equations. Hence, whenever we have this difficulty in expressing from the fundamental definitions, we have the empirical correlations. We have the empirical correlations. So we have the empirical correlations for FFW, that is frictional forces between the gas and wall per unit volume. We have the empirical correlations available. We don't have any standard theoretical correlations, theoretical expression derived from the fundamentals. We don't have. So we have to use only empirical correlations for this term. That is frictional forces between the solid and wall per unit volume.
Sir,
Sorry. So that is about the frictional forces between gas and wall. And I have an expressions which I will show in the next slide. Okay, I have this empirical expressions in the next slide. I will show it. How to move this? So I just have to erase because I think mistakenly I wrote here. Hope you understood. Since this is frictional force per volume, you don't have any. Yes, please.
sir, in the first and second bullet point, the areas will be different, right?
Where?
Sir, for the net pressure force, the area would be like of the cross-sectional area, but for the gas wall friction, it will be like the wall area in which the gas is in contact with, right?
Okay, but we won't talk about the only area near the wall. We'll talk about the throughout area, because why do we take that one? Why do we take the overall area? That's important point. Thank you. So this is the fluid is flowing, right? Let's say some particle is here, and this is fluid particle. Okay, this is not the solid particle. Just for explanation, maybe I'll change the color. We won't talk about, the question is, I think I'll repeat the question. Here the frictional losses, gas wall frictional loss nearly takes place near the wall. So you want me to consider only area near the wall, right? Why are we considering the overall cross-sectional area? Am I right? Is it
Yes,
your
sir.
question? Yeah.
Yes, sir.
Okay. So here I'm explaining you that these are not the solid particles. Let's say this is fluid particle. Just for explanation point of view. Okay. Now let's say these particles are there, and this is something here. So while it moves, while this fluid moves, let's say the particle 1, this is particle 2, this is particle 3, this is particle 4. Do you think the position of these particles will be remain same as it moves? Is the particle 1 move, when it come here, will be remains 1 or something else?
It will change.
The student who asked question can unmute and tell me.
So it will change, sir.
It will change, because not necessarily it will be 1. It can be particle number 2 can come here and hit, and after some time particle 3 can come here and hit, and here particle 1 can come and hit. So the particles tend to move, intermix. So if I take only area near this, I will not be able to cover all the fluid particles. I will not be able to cover the all whole particles. Since the particles will mix, I need to consider the overall this thing. Overall cross-section area. I need to take the overall effects. Since overall effects vary from position to position, we are taking the small element. Where we assume that all these interactions are uniform. That is the where we are taking the small element. Otherwise, we don't need to take the small element. That are the assumptions we are making. Since we are making the assumptions, often this won't match with the experimental results. That is why they are conducting experimental results and getting the proportionality constants in the form of empirical relationships. That is why we take the small element. Because of making these assumptions, we get an error. To nullify those errors, we are using the empirical relationships than the actual relationships. Do you understood my explanation, or did I answer your question?
Sir, means like some kind of shear forces that will be near the wall that we are not considering here, right?
We are
This will be
considering
like
that
a
also.
total fix. Acha, everything is considered in FFW.
Yes, everything in the cross section is considered.
Okay,
Because
sir.
the particles are moving, intermixing randomly.
Okay, sir.
That's why I have taken the cross sectional area.
Yes.
Since we are talking about the overall total volume of the element, that is why instead of talking about only area, we have to consider the volume of the element, because we want to give the overall volume of the element.
Okay, sir.
That's why FFW includes all the changes takes place in the overall element. That's why we have defined FFW as frictional force per volume. That's why FFW is plus volume. That's why we need to multiply with the volume, and the volume is nothing but A into delta L. Thank you for raising this, and I think other students will also get benefit by that explanation. So similarly, we have the net solid to wall frictional forces. My God, time is running. So just like gas wall frictional forces, we have FPW, that is solid wall frictional forces per unit volume. There we have considered the interactions of the solid particles with surface throughout the volume of the element. Hence, we have multiplied with the volume of the element is A into delta L. And gravitational forces is nothing but the gravitational force offered by the gas and gravitational force offered by the solid. This is solid, because within this element we have gas and we have the solid. The net gravitational force will be the gravitational force offered by the gas and gravitational force offered by the solid. And we know gravitational force is nothing but m into g. The m refers to mass of gas in that element. And in case of solids, the m refers to mass of particles in the element. Mass of the particles in the element into g. So gravitational force is mg. So in case of gravitational force offered by the gas, m refers to mass of gas in the element. In case of gravitational force offered by the solids, m refers to the mass of particles in the element. So how do you find out the mass of the element? We know delta V, that is the volume of small element. If I multiply with density, I get m. If I multiply with density, I get m. So now if I want to know m of the gas, this I have to multiply with the void volume. So delta V is nothing but A into delta L, cross sectional area into small element length, that is delta V. And here we have epsilon, void volume, because gas is there in the void spaces. And we have the density of the fluid, and G. Since this inclined wall, we need to take the this component sin theta. We need to incorporate the sin theta. The fluid is flowing in this direction, but gravitational force acting only in the normal direction. So this is the theta. So we are considering the sin theta term here. Similarly, mass of particles in the element, volume of the element, solid volume, that is 1 minus epsilon into particle density of 2 times g, I think that is mistake, g into sine theta. The next one, rate of increase in momentum of the gas. Rate of increase in the momentum of gas. Rate of increase in momentum of gas. So rate of increase in momentum is nothing but mass flow rate into velocity. The change in momentum can be estimated. The rate of change in momentum can be estimated in change in, that is momentum at the inlet minus momentum at the outlet. Momentum can be change in rate of momentum can be rate of change in momentum can be mass flow rate into velocity. So here I just put m dot. M dot is usually mass flow rate. The m dot we are writing as mf. That's why I have written, okay. So please try to understand m dot. mf is nothing but the mass flow rate. Just to represent that one, I have kept m dot in the brackets. mf is nothing but the m dot. Just to represent that one, I kept this one in brackets. And we already learned this. Oh, God. Okay. So we already learned that m dot is nothing but a into uf into epsilon into rho f. That is the mf. For mp, a into up into 1 minus epsilon into rho p. So I have just substituted this expression here. I have just substituted that expression here. mf is nothing but a into uf into epsilon into rho f into change in, because we have done the change in, right? Change in. So we have the delta uf. So that way we get the rate of increase in momentum of gas. Then we have the rate of increase in momentum of the particles, that is mp into delta up, mp into delta up. So we get a into up into 1 minus epsilon into rho p into delta up. Now if I substitute all these forces in the force balance expression, which I showed in the previous slide, that is pressure force, that is interaction between the gas and wall, interaction between the solid and wall, gravitational force offered by the fluid gas, gravitational force offered by the solids. I think I just copy pasted that one. So then rate of increase in the momentum of the gas, rate of increase in the momentum of the particles. If I integrate this one, I'll get the final pressure drop expression. If I integrate this one, I'll get the final pressure drop expression. So first of all, every term has a. Every term has a cross section area. A here, A here, A here, A here. Every term has a. So we can cancel a term in the throughout the expression. Then we get the final pressure drop expression. P1 is the inlet pressure and P2 is the outlet pressure. The P1 minus P2 is nothing but delta. P1 minus P2 is nothing but the delta P. So we have the sorry, there is some issues. This is the subscript. This is the subscript. I think rest of the equations the same. Fine. So frictional losses between the fluid and wall, FW. Frictional losses between the particle and wall. Gravitational force term. Gravitational force by the gas. Gravitational force by the particles. Rate of change in momentum of the gas. Rate of change in momentum of the particles. Right? So always not necessarily that we need to use all the terms. Let's say the pipe is horizontal. Let's say the pipe is horizontal. then we don't need to use the gravitational term. We don't need to use the gravitational term. Sin theta, because sin theta is 0, sin 0 is 0. So these two terms can be neglected. These terms can be neglected. And let's say we take two cases. There is one pipe. I'm giving the two simple cases. In the first case, this is the solid feed. The solids are feeding. The solids are just supplied. So the solids are falling. So the solids are falling. Now to transport the solids, we are supplying gas. To transport the solids, we are supplying this gas. The gas velocity or the certain amount of gas, the energy of certain amount of energy of the gas will be utilized to accelerate the particles. Hence, the particles are moving. As the fluid flows. We are introducing the gas. We are blowing the gas with certain velocity. So some amount of energy of the gas will be utilized to accelerate the particles so that the particles can move along with the fluid. That is the case A. Sorry. Let's say this is the case A. I have a case B. Right? I have a blower here. This is connected to a blower. I need to blow the gas. Right? I need to blow the gas. Actually, the particles are coming from somewhere. The fluid particle suspension is coming from somewhere. The fluid particles are suspension is coming from somewhere. And now this is I'm only interested in the pressure drop from here to here. I'm interested only pressure drop from here to here. In this case also, I'm only interested to estimate the pressure drop only in this case. Right? So the fluid particle suspension is coming from somewhere. We have blown. We have given some energy with help of this blower. And particles are further flowing. Let's say we are not having any blower. Forget about blower. So this is pipeline. The particles are coming from somewhere. We are not touching blower, and they're moving. They are moving. So this is case A. So this is the case A, where we are blowing the gas at this starting point to give some energy to accelerate the particles. In the case B, this is the case B. The particles and fluid is coming from somewhere. The suspension is coming somewhere and moving. But I am interested to only estimate the pressure drop from here to here. Now, for case A, what are all the terms I need to consider? Here we have the term 1. Let's say this is term 2, term 3, term 4, term 5, term 6. We have 6 terms. Each term its own significance I've explained already. Now, maybe can someone tell me Can someone tell me in case of case A, somebody have questions? Huh? Can someone tell me in case of case A, what are all the terms I will have to include? Maybe I'll ask one or two. Arjun Gupta, are you there? Arjun Gupta.
Yes, sir.
Arjun Gupta.
Yes, sir.
In case of case A, to estimate the pressure drop, what are all the terms I will include? Like 1, 2, 3, 4, 5, 6 are there. What are the terms I need to include? I shall include to estimate the pressure drop. Like
Sir,
we have the
3,
first.
4,
Yeah.
5, 6. 3, 4,
Sorry?
5, 6. 3, 4,
3,
5,
4.
6.
3, 4, 5, 6. I shall include. What about 1 and 2?
Sir, confused.
What
I
is
think,
1?
sir.
Do you remember what is 1? First one is the frictional loss between the fluid and the wall.
And
So
the pressure loss.
do we need to include that one or not? Frictional losses need included or not in this case A?
The solids are coming.
The solids are fed and the gas is blown, and I need to estimate the pressure losses from here to here. So will there be any frictional losses or not? What happened? Students are leaving.
Sir, 1, 2, and 5, I guess. This term should be included.
Who is answering?
Sir,
Aryan
Subhajit.
Gupta or someone else?
No, Subhajit, sir.
But I didn't ask you, Subhajit. I'm discussing with Aryan. Yeah,
Sorry,
thank
sir.
you. Yeah, Aryan, please unmute. So,
Yes, sir.
always we need to consider frictional losses. We can never neglect the frictional losses.
Okay, sir.
Frictional losses between fluid and wall, frictional loss between particle and wall, always we need to consider. Now, the term 3, gravitational force. Will this effect will be there? The gravitational force effect will be there in the case A.
No,
Here,
sir.
because theta is 0. So 3 and 4 we would not consider. 5. Are we accelerating the particles with help of gas or not? Means are we giving some momentum for the particles with help of gas?
Yes, sir.
Yes, so we need to consider 5 and we need to consider the 6. Thank you, Aryan.
Thank you, sir.
So maybe I'll ask someone. Pradeep Kumar. Pradeep Kumar, are you there? Are you absent or what? Just joined and left? I'm not considering any marks, anything. Just asking. Just simple interaction. Pradeep Kumar, are you there? 108. So those who are leaving now, I will have to cut their marks. Because as soon as I ask questions, somebody leaves. This is not a network problem. Okay, Neha Gupta. Pradeep Kumar is absent. Neha Gupta. Neha Gupta is absent. Okay. Anyway, you all know that attendance log will be there, right? When you leave, when you join, everything will be logged in Teams. So I can know exactly at 1 hour 30 minutes who left. I'm actually recording that. This is really not good. I didn't expect this. If you don't know, you don't know. If you don't understand, you don't understand. Why you have to? So, okay. Harsh Verma, are you there? Harsh Verma. He's also not there, right? Jayanand.
Yes, sir. Hello.
Yes, Jaya. Sorry, I think Jaya told Jaya. So in the case B, what are we doing in case B? What do we need to find out? Can you explain?
So the third and fourth term, both of them will be zero, and the sixth term will also be zero because we are not giving any velocity to the particles.
Right. What about fifth term?
So the gas molecules they are getting energy by the blower, so it will be
So
present.
yeah, I haven't. That's why later I cut the blower part. So I'm not considering the blower part. So I'm saying initially I told we are giving energy to the blower, but later I said no blower is there. So let's say there is no blower. I just want to measure pressure drop. What are the terms? I think you understood.
Sir, so fifth term will also become zero, and
Yes,
we will consider one, two, and just two terms.
that's all. Very good. I'm so happy, Jay. So since the suspense
Sir,
is
I have a
already
question, sir.
yes, Subodh. Yes.
Sir, means in case B there is no fluid coming in, right?
In case of no fluid coming
In
in,
case,
okay.
oh, okay.
Because if I this is basically pressure drop from which point to which point, that only matters. If I this is my one, I don't need to consider the moment of acceleration, the rate of momentum change, because they're already being accelerated. They're already being accelerated. That's why in case of case B, since my interest is pressure drop between these 2 points, I will have to consider only term 1 and term 2.
Okay, sir, got
I
it.
think it is good time to time calling the students' names. Then we will know who are actually there. I didn't know that the online teaching can go to this extent. Right. Anyway, not much frustrations. That is fine. So this is the way we will estimate pressure drop, and this is the way we will consider the importance of these terms. So here in the previous one we have the 2 terms, unknown terms. That is FFFW, FPW. How to find out what are the empirical correlations for the solid wall frictional forces. For the solid wall frictional forces per volume, FPW, we will use these correlations. So Kono and Saito, they have derived this correlation for vertical dilute phase pneumatic transport So we will use this correlation for the vertical phase dilating vertical type dilute pneumatic transport. So in this, so far I have shown the correlations for choking velocity UCH, and I have also given correlations for salting velocity. And here I am given for the correlations for FPWL. Whenever we use any empirical correlations, it will have some empirical constant. These constants are not dimensionless, they are dimensional. Whenever we have the empirical correlation, some empirical correlation will be non-dimensional, some empirical correlation will be dimensional. So here we can definitely say this is non-dimensional, either left-hand side or right-hand side. So whenever we have the dimensional empirical correlations, whatever units they specify to use, we need to use same units. Okay. Always remember, whenever you take any empirical correlations from any reference book or any paper or anything, we have to see whether it is dimensional or non-dimensional. If it is dimensionless, then you don't worry about units. But if it is dimensional empirical correlation, that is, it is not a non-dimensional correlation, then we have to stick to the units, whether it is FES units, SI units, or whether it's mixture of units. We have to refer to that information and we have to follow it. So whatever correlations I have given in this topic, you need to use SI units. You need to use SI units because these are all dimensional correlations. It has dimensions. So they mentioned that in the book that we need to use SI units. In the book I shared with all of you in the last week, they mentioned that we need to use SI units. Means diameter has to be in meters. And the G is nothing but mass flux, that is kg per meter square second. Kg per meter square second. If you use wrong units, you will get totally wrong values. If you use wrong units, you will get the totally wrong values, wrong answers. Please note this point that you will have to use SI units for all the correlations in this topic only. In today's lecture slides, in yesterday last class slides, whatever correlations I am showing, they strictly need to use SI units. For horizontal dilute pneumatic transport, this is for vertical, this expression. For horizontal, we have this expression. In horizontal, we have one unknown term, that is FP. 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 So FP can be expressed using this. FP can be expressed, can be calculated from this correlation, that is Hinckel correlation. Similarly, UP, we only know superficial velocity of the gas, and we don't know what velocity it attained because of the acceleration, or what velocity it attained in a horizontal pipe. We have another correlation. We have another correlation, that is UP equal to this one. UP, if you want to use horizontal dilute pneumatic transport, you can estimate the UP using this expression. UP using this expression. Now here, the FP, the friction factor between solid wall, has another unknown term called CD. Here, density of the fluid, density of the particles, diameter of the pipe, diameter of the particle, X is diameter of the particle, UF is velocity of the fluid, UP is velocity of the particle, but one unknown term is CD. The CD is estimated, CD is nothing but the drag coefficient. The CD is nothing but the drag coefficient. The drag coefficient can be estimated using these expressions. However, this is specific to Reynolds number, REP. REP is estimated using this expression. REP is estimated using this expression. So, based on, once we calculate Reynolds number, Based on the Reynolds number range, we select the CD value. Then we substitute the CD value here to find out FP. Similarly, gas-solid frictional forces, we're assuming that since the particles are dilute, low concentration, so the presence of particle doesn't affect the behavior of the gas. We assume that. In reality, that will be there. We're assuming that to make our life simple. Assuming the low concentration particles, the presence of particle doesn't affect the gas behavior. Hence, FFWL will be estimated using the 2FG fanning friction factor into rho g velocity of the fluid square into L by D. This we will definitely see in the fluid mechanics. Definitely you will see in the fluid mechanics. So in the previous slide I have shown FPW, and in this slide I have shown the FFW. So this way we will be able to calculate the total pressure drop which is given in this expression. The total pressure drop given in this expression. So often we need to use bends. Often we need to use bends because you have a horizontal pipe, then you will have a vertical pipe. To combine these pipes, we have to use bends. We have to use bends. Whenever the fluid flows, the frictional losses in the bends will be much higher. The frictional losses in the bends will be much higher because of the boundary layer separation. Because of the boundary layer separation. But what problem happens when there is a particles? When there is a particles, what will happen is because of the boundary layer separation, the particles tends to accumulate. The particles tend to accumulate here. The particles tend to accumulate here and causes the blockage. Causes the blockage of the flow, and it can greatly increase the pressure drop. So people propose that to decrease the settling of particles, they suggested to use. Sorry, I had to draw manually. That's how it is like this. Oh, this is the bend, just smooth bend. Okay, it will never have bend like they were drawn. So if the angle of this is high, then what will happen? You can reduce the settling. So through this way, the pressure losses of the settling of solids are minimized. But later, Jenge proposed use of blind tees, especially for the solids. Whenever there is presence of solids, he proposed to use the blind tees, blind T joints. What is blind T joint? You will have an additional cross section. Which is closed. This is called blind tees, which is closed. So whenever the fluid, normally T joint will be like this. But in case of blind tees, you will have an additional small cross section, which will be closed. So what will happen is that since this is closed, the particles will come and settle. Since this is closed, the particles will come and close. After some time, this whole area is filled with particles. Since particle-particle interactions are much lower compared to the particle and solid, that causes the particle cushion. And this minimizes the pressure drop. Greatly. Use of blind tees reduces the pressure drop greatly because of this particle cushioning effect. The particle cushioning effect coming from the particle settled in this zone. So pressure drop in the bends is basically 7.5 times the vertical pressure drop. Vertical pressure drop means delta P by L. Here, delta P vertical divided by L. Delta per 1 meter or 1 per meter meter distance, how much pressure drop is required. If suppose the fluid is flowing, if the particle and gas is flowing in a vertical pipe, if you can measure delta P of a 1 meter pipe, delta P of a 1 meter pipe. How much delta P takes place in this vertical pipe of 1 meter length? If you multiply with 7.5 times, that will be pressure drop in one bend. Pressure drop in one bend, not bends, one bend. In one bend. So this way we can know the pressure drop across the bend. So I have talked about pressure drop, I have talked about blower, I have talked about how to attain the dilute phase transport. And this is the typical diagram for the dilute phase pneumatic transport. This is the blower. The blower sends the gas with certain flow rate, usually air, and the solid stored in silo will be gradually supplied to this pipeline with help of rotary valve. I have explained in last class or earlier classes how this rotary valve used to get a regulated mass flow to the particles. So the blower carries the particles, the blowing gas carries the particles. That's what we have seen so far. And this is the conveying line from which point to which point. Since we need to separate the particles from the gas, often we use a separator. The separator separates the particles from the air. The separator, we will see later in this course how the separator works and all, what the different types of separators used to separate particles from the gas. That will be later part of the course. So these particles are collected and the particles separated and falls down, and the gas moves upward. That way, the particles are transported from this silo to this process. So we just shown very small length, but often this will be 30 meters, 40 meters, 100 meters, depends upon the requirement. So this is all about the dilute phase pneumatic transport. So I wanted to solve one quick problem. I think we have roughly 7 minutes. Let's see how much we can do. So this is the problem statement 1. So we need to design a dilute phase pneumatic transport system. We need to design a dilute phase pneumatic transport system to transport 900 kgs per hour of sand particles. 900 kgs per hour of sand particles having the density 2500 kg per meter cube, having density 2500 kg per meter cube, and the mean particle size is 1000 microns between the 2 points in a plant, in industry, between 2 points in a plant, separated by 30-meter horizontal distance. 30-meter horizontal distance using ambient air. So they're saying that they have the allowable pressure losses is 0.55 bar. So we need to design a dilute phase pneumatic transport system such that this much amount of particles are transported with this pressure losses, within this pressure losses. If the design system is giving pressure losses higher than this, definitely your design system cannot be used in that specific industry. So let's solve this problem. Hope you're able to see my Excel sheet.
Yes, sir.
So I need to transport mass flow rate solids. I need to transport this much amount of solids, that is 900 kgs per hour. We need to use SI units, so I will convert into kgs per second. That is 1 hour equal to 3600 seconds. I will have 0.25 kgs per second mass flow rate. Then particle density. Particle density is 2500 kg per meter cube. This is in SI units, so I can leave it as it is. Then that is whatever information given, mean particle size. Particle size 100 microns. Units we use meters. So see 100 microns, 100 micrometers. 1 meter equal to 10 to the power of 6 microns. So I have to divide this 10 to the power of 6, 1e6. That is 0.301. This many meters. That is the particle size. So particle size x and density is den underscore p in the expressions rho p. In the expressions rho p, and this is mp. This is given. Design a dilute-based pneumatic transport system to transport 900 kg per hour sand particles having 2500 kg per meter cube density and having the particles as 100 microns. And we need to use horizontal pipe having a distance of 30 meters. We need to design horizontal. There's a horizontal pipe. So the length is basically L is 30 meters. Allowable del P. Allowable del P is 0.55 bar. So properties of air, they said air is used as a gas to blow the particles. Air density we can use is not specified, so I will use the standard air density and air viscosity. Air density often referred as 1 kg per meter cube. Air density is 1 kg per meter cube. If they don't specify, you can use it. For water, 1000 kg per meter cube. For air, 1 kg per meter cube. If they specify these values, you use it. If not specified, always you can approximate, because the ambient temperature will be roughly 1 kg per meter cube. Air viscosity is 1 cp, 1 centipoise. 1 centipoise. If they don't specify, you can assume as a 1 centipoise. 1 centipoise equal to 1 over 1000. 1 over 1000 kg per meter second. Units of viscosity in SI units will be kg per meter second. Units of viscosity in SI units is this one. So the first step is we need to select the pipe size, right? Through which pipe we are pumping this, we are blowing these gas particles. We need to select the pipe size. The pipe sizes, we have the standard pipe sizes. We have the standard pipe sizes starting from half inch, 3/4 inch, 1 inch, 2 inch, 2 inch, and 3 inch. We have like this standard pipe sizes, and we know 0.5, 0.75, 1, 2, 3. We know that 1 inch equal to 25.4 mm. 1 inch equal to 25.4 mm. So this many mm, that is the size. So this is the mm of the pipe. Okay. So we have to select one. We have to select one out of this. Of course, we have 4 inch other pipes also there. We have select one, and we have to design, and we have to estimate the pressure drop, and we have to see the estimated pressure drop is lower than this or not. If it comes to lower than this, then your system is right. If your assumed values are coming greater than 1, then you have to do the recalculation. Such that you will get the final delta pressure comes to be lower than 0.55 bar. Okay. I will just save it before I move on. Dilute. So in step 2, we have to find out what is the solvation velocity. Because since for horizontal pipe we have the solvation velocity and superficial velocity has to be U, Fs has to be 1.5 times U solvation velocity. Right? So for solvation velocity for vertical pipe, we have this expression. To calculate the solvation velocity. Right? So we can rearrange this expression that we can bring the U salt here. Then you will get 1100 x plus 3.5. We can bring up all other factors here. So I will do that. MP by density of fluid into cross-sectional area. So yeah, so now we have to select a pipe. I'm selecting the 3-inch pipe. I can select any one, so I'm selecting 3-inch pipe. So since I select a 3-inch pipe, I can calculate area. How do I calculate area? Pi by 4 d square. Pi into d square. That is, this is the diameter, but I need to convert into meters. So divided by 1000 by 4. So this is the area in meters square.
Sir,
Yes, please.
sir, so in questions of this type, then we will directly take anytime the pipe with maximum diameter, right? Like, since the
Not-
diameter is proportional to
Not
pressure
necessarily. Not necessarily we will take the maximum. In the after saltation velocity, we get the superficial velocity. No? The superficial velocity has to be higher than or around 15. It should be 10 to 15. Accordingly, we have, if it comes to be very low, then we have to change here. I have started with 3-inch pipe. As an initial approximation, the superficial velocity should be 10 to 15 meter per second. Okay. So after calculating salting velocity, if it comes to be, let's say, less than 10, then I need to recheck the value at the initial case.
Okay, sir.
So I'm just calculating this expression MP by density of fluid into A. So this will be MP is this divided by density into area. So I have used this, then I got this. You can see mass flow rate by density, A density, and we have the area. Then I have 10 to the power of 1440x plus 1.96. This term I am calculating. So this will be 10 to the power of 1440 multiplied by x. X is diameter. So I am selecting this plus 1.96. Oh. I didn't put the brackets. So this one, 10 to the power of 1440 into x. X is the mean particle size plus 1.96. Then I have square root of g into d to the power of 1100 x plus 2.5. I'm just doing this part. So this will be SQRT square root. In Excel we can use SQRT. 9.81 into d diameter. So this is the diameter. So this is the square root term.
Sir,
And
sorry
the
to
power of-
interrupt, but we have another class right now.
Oh, okay. I'll stop in 1 minute. I'll just finish this salting velocity and we'll stop. Sorry. Thank you for reminding. 1100 into x plus 2.5. Square root of g into d to the power of 1100 plus 2.5. I'm sorry. I'll just stop it here. So here I have to find out the salting velocity. So u salt to the power of 1100 x plus 2.5. If I bring u salt from the left hand side to right hand side, I will have u salt. That will become what? That will become, we can add powers, right? We can add powers. So that will become 3.5. So this will be equal to, we need to multiply all this thing. We need to multiply by first term multiplied by second term multiplied by third term. I have this. So I have to do 1100 x plus 3.5. This will be 1100 into x is this one plus 3.5. So the u salt will be this to the power of 1 over this salting velocity meter per second. I'll upload this and we may cross check later. U superficial gas velocity. U superficial will be 1.5 times of this. 1.5 times this. So 15.66. This is coming around 10 to 15. That means my initial assumption could be acceptable. Not sure, could be acceptable. We'll only finalize after calculating the delta P. So we'll continue from here. Thank you and sorry, I didn't actually notice the time, and I'm very sorry for taking extra 10 minutes. Yeah, thank you, students. You may join your next class. If student doesn't have any next class, if they have doubts, they can stay back and ask me questions.
Sir, I have a doubt.
Yes, Sripad.
Yes, sir. Sir, I could not understand why the particle velocity 0 in the B case.
Where? In this case, here.
Yes, sir.
Oh, particle velocity is not 0. But we are not accelerating. We are not giving any additional energy for the acceleration. Acceleration is rate of change of momentum, right? So
yes,
whatever is coming, it got accelerated somewhere else. Here the fluid is coming from somewhere, right? This got
yes,
accelerated already at some point of time. So we are not giving any additional energy in this point because we are measuring only pressure drop from here to here. So we are not giving any additional energy for the acceleration. Hence, we are neglecting the 5 and 6 terms.
Okay, sir.
So suppose let me give an example. Let's say this is a pipe, right? This is a horizontal pipe. Then we have the vertical pipe. So when we want to design it, we have blow the air at the entrance. So we have given certain acceleration to the particles. the air is coming and flowing along this vertical pipe. Now I want to calculate pressure drop from here. This is the entrance, this is the exit. So I have an expressions for horizontal pipe and I have expressions for the vertical pipe. When I do the calculations for the vertical pipe, I don't need to again include the rate of change of momentum. Do you understood what I'm trying to say?
Yes, sir. I understood.
We are assuming that there's a continuous. First horizontal is there, then bend came, then vertical is there. First of all, I've calculated the pressure drop across horizontal. At that time, I have included the rate of change of momentum. But when I want to consider the pressure drop across vertical pipe, I don't need to again consider that rate of change of momentum because the particles are already accelerated at the beginning.
Yes, sir.
Because the correlations for this are different, the correlations for this are different. That's where we have to be a little bit careful in using these expressions.
Okay.
Hope you understood what I'm trying to say.
Yes, sir. I understood now.
Okay. Yeah, thank you.
Thank you.
If any other students, I'm happy to take your questions. Kindly ask me. If no questions, you may leave. Thank you so much.
Thank you, sir.
Aryan, you have a question? Yeah, thank you, Aman. Please leave the meeting if you don't have questions because I want to see who are just turning on the Teams and leaving. So if you're not leaving me, say assume that you are not present physically in front of your device.